And welcome everybody. So Armand, I'm making you co-host in case that you see that anybody needs to be let in, okay? You're in charge of that. Is that okay?
Yeah, I can do that.
All right, good. That way I don't have that many windows open.
All right.
All right, so this is the Miller Index. I was gonna take you guys back to this slides for the Miller Index, and you can see my pointer, right? In this case, we have that the 111 is the one that passes. This is the plane 111, and it would pass through this unit cell like this cubic unit cell. It touches this, and this atom. What that means is that there's a plane, an infinite plane that passes there. And there's actually a family of planes that passes there. Then there's another one here, and they're all parallel to each other in that direction. So I hope that that's clear. And also how we get it to be 111. What is the meaning of 111? Okay. So if you have questions about this, ask me now, because I think it's important to be able to visualize it before moving forward. Then I have another one right here. For instance, this one is the 1/2. It intercepts the axis at 1/2, 0, 0, and at 0, 1, 0. So I see this plane right here, right? So this plane doesn't touch a lattice point right here. It's halfway between the lattice points. What that means is that that is the x-intercept. So now you take the reciprocal of 1/2 and you get 2. So now you have that the Miller index is 2. Then the 1 is because it passes through the 1 in the y direction, and 0 because it does, this actual plane doesn't pass through this point in the c-axis, doesn't touch the c-axis, the one that passes through the unit cell right there. But there's actually another plane behind it. Would the other plane pass through the c-axis? The family of planes that are 2, 1, 0, this particular one that I'm highlighting here passes through 1/2, 0, 0, and from 0, 1, 0. How about the plane behind it? Would that one pass through the c-axis or not? So do I have a volunteer to answer that question? Yes, no?
I think it would, but I'm not exactly sure what the question was. If you could.
So right, so if I have another plane, right? The plane, so there's this plane, the one, the 2, 1, 0. It's
Yeah.
actually a whole family of planes.
Oh wait, yeah. So none of those planes would ever touch the z-axis because they're all parallel, right?
Well, it's parallel to this one, right? So for
Mhm.
instance, there's this one right here, the one, the 2, 1, 0. So in
Yeah.
that family of planes, the actual plane that this one passes through here, is there a plane that passes through the 0, 0, 0 point?
Oh, yes, that's possible.
Ah.
0, 0, 0.
Yeah. 0, 0, 0
That's
is
possible. Yes.
possible, I
Okay,
guess.
that's possible, right? And then there's going to be another one that is going to pass parallel to this one that is highlighted, that is going to pass through 1, 0, 0. And then in this direction, it's going to pass through where? In the, at what point here in this line does it pass through, right?
3/2.
1/2, 1, 0.
Who said 1/2? I don't see the highlighted.
Exactly. It should be 1/2 x, and then 1 y, and then 0 x z.
Right. So then you have all of that family of planes that is passing by. It's just in this unit cell that we're highlighting this part, but this is almost an infinite, is actually an infinite plane. And then there's a family of them that are separated behind it by a particular distance. So that's clear for everybody then. All right, so then let me move to this one. It's a little bit different coloration. All right, so sorry, 3, 4. So here, this is from an actual paper that they drew it like this. This is the 1, 0, 2. And these are several unit cells together. But now you can see that it's passing through and cutting through this and this point and this point and this point. So that's the actual plane that is passing through. So in this case, this particular plane doesn't pass through the y-axis, right? Ever. But then there's a plane behind it that is going to pass nearby, and then another plane behind this one that is going to be passing through the y-axis, but this one doesn't pass through it. And you can see which atoms on that surface are going to be popping out. These 3 atoms, for instance, are going to be shown, and these 3 atoms are going to be shown. But this one is below that surface, so that one is in the portion below. Here's another picture of it. This is another example. This is a little bit different because it's not leaning in the same direction. Now it's leaning in the opposite direction. So let me go back and forth. Back. That one is pointed like this. This one is pointed like this. So one is like this. The other one is like this, right? So the main difference is that this one has that the intercept is in the negative x direction. So here's the intercept. For that intercept being negative, what that means is that this Miller index has a -1. And the way that we define it is that we don't put a -1, 0, 2. We just put a little bar on the top. And that tells you that that's the one pointing so that it's in the negative intercept. And that's a convention that is used by the literature too.
Is there a relation between these two in terms of the angle between them? Like, because it looks like that they have a 90-degree angle between them. I mean, it looks like, but I'm not sure.
So they're different cuts of the same, right? So they should be like this.
Right, so they're like perpendicular planes to each other.
Exactly.
Okay.
All right, so then here's just different ones. This one intercepts in the 3A, 2B, and 2C. So that means that that one is the 233 Miller index, depending on XYZ that you have. This one is the 100. This is the 200. So you see this one is 100 because its intercept is right at the 1 in the x direction. This one is in the 1/2 00, 1/2 in the x direction. So that one is the 200. This one back here is similar to this one, the 100 and the negative, the bar 100. They're almost the same. They're just one is behind the other like this. Questions?
It really looks like that 100 and 200 are on the same family.
So the 200 is located halfway through. So if we look at the family of the 100, it's going to be one at 100, and then the next one is going to appear at the 000.
Oh, okay. So I mean,
so the 200 plane is halfway in between those two.
Oh, okay. That's kind of, I had a misunderstanding that all the planes that are parallel are in the same family, but I guess that's not the case.
No, because the 200 family is going to have more planes than the 100, right? Because they're acting closer together.
Yeah, double number of planes. And so, yeah, we can calculate the interplanar distance of the same family. And if we do that, we'll find that 200 is closer than the next member of 100 should be.
Right. So the 100 distance between planes is 1. The 200 distance between planes is 1/2.
Okay, that makes sense. Yeah, I had a misunderstanding.
And everybody in the 100 is inside of the 200 family.
Yeah, it's a subset of 200. Yeah.
So what is the difference between 100 and 1 bar 00?
All right, so the difference between 100 and 1 bar 00 they're almost identical, except that one is this back facet, right? So when would you use the bar ones? If you were talking about a slab that has this size, maybe you want to have, so let's say something that had two elements in it, like zinc oxide. You could have that the zinc and the oxide are going to be on the top is oxygens and then zincs and then oxygens and then zincs in kind of like planes like this, right? So it could be that the 100 corresponds to the top being oxygen. So this surface 100 has oxygens. And this surface, the bar 00 has zincs on that surface. So they're not exactly the same, but they could be if there's no difference between the atoms inside of them.
Thank you.
And when you're thinking about slabs, they're different in that direction, particularly. But if it's a bulk one, it's not going to be a difference. So if you're looking at the 100 surface, it could be that this is the zinc facet and this one would be the oxygen facet, something like that.
Dr. Bunda, you use the
ahead.
same bars for the A's, A, B, and C's too.
I'm sorry?
If you look at the for the plane intercept axis, you use those bars for A, B, and C too. And at the same time, you used it for the Miller index at the end too with one bar.
Oh, I think those are supposed to be vectors. Sorry, that's supposed to be an arrow vector, but it doesn't.
So this one bar 00 is not a vector, right? Your definition here is
family
different.
of planes. Yeah.
Oh, okay.
Yeah. So now,
excuse me.
Go ahead.
Yeah, I mean, in the previous slide, you said that family, I mean, 100 is the family of 200 or like that, right?
No, so let me go into families now.
Yeah. I mean,
This
like, I couldn't understand it.
This 100 is related to all of the possible permutations with 1 and -1. So this 100 has all of these guys inside of it, this family.
Oh, you define that way, yeah.
That's the family.
Okay.
So all of those planes are equivalent from a rotational symmetry point of view. So if you have a slab and you have the 100 over here and you rotate it, you're going to get now the bar 100 and so forth. Now, what I was saying
there is a 200, right?
The 200 is going to be, you're going to have the family of planes. So the 200, or maybe I have to be careful here. What I mean is that there's all of these planes, right? That are cutting through an infinite number of planes cutting to your crystal with that same direction. The 100 planes are separated by a distance of 1. Yes, now the 20 planes are separated by a distance of half. So you're gonna have like in between all of those, there's more planes than here. So they're not an identical family, but all of the ones that show up in the 100 family are gonna be inside of the 200 family. Does that make sense?
Yeah, what I was thinking, like 200 is the like family member of the 100, right? Like because 200 like comes fast, right? I mean earlier, right? That's a
no. The 100 is here at 100, and then it's the 100 is here at 1, and then there's another one that is a distance 1 away, and then there's another one that is a -1 from 0 away, and then -2 and so forth. Now, if this one is 1 and this one is 0. The 200 is halfway in between.
So if we see them as sets, we'll say that the family of 200 have double elements than 100. So the main difference is the amount of elements, even though that 100 is contained in 200 in this case. 200 has.
Yeah, so
that is what I was
contains
thinking,
the
like,
100, but not the other way around.
Yeah. Okay. Thank you.
Then we have, I talked to you guys about that there's 14 Bravais lattices. And I have some pictures here. So you have the cubic, the simple cubic. a body center cubic, and a face center cubic. Then if one of the three directions is not equivalent, in this case, A and B are equivalent, but C is not, then you have tetratagonal. If A, B, and C are not identical, but the angle between them is 90 degrees, you have orthorhombic. So I don't know if you remember, there was somebody asking about orthorhombic back in one of the colloquiums, right? What is orthorhombic? Here is that particular Bravais lattice, and so forth. So let me go over something that this I already covered, the coordination number, but this I haven't covered, the atomic packing factor. So
Dr. Brenda,
yeah, go ahead.
quick question before we move on from the Miller indices.
Mhm.
I've seen in like papers Miller indices with 4 terms, like a
Yeah.
1, 0, 1
Yeah,
bar 0.
exactly. When
What
you
is that?
have a hexagonal one,
Mhm.
a hexagonal unit cell, then you actually need a fourth index to describe which surface you're looking at. The normal ones that we are familiar with, like the cubic, orthorhombic, all of those, you only need 3 numbers. You actually need a fourth one for the hexagonal one. That's the reason that you see that.
So the first 3 are the A, B, and C axis. What would that fourth term represent?
The
It
angle?
tells you which part of the surface you're looking at. Which, yeah.
Okay. Okay.
Sorry, if I can ask,
Yeah.
isn't in the hexagonal, the first 3, one of them is determined by the other 2? Like it's just a convention that we use 4 numbers, but we could use 3, but it's easier to understand with 4?
I think you're correct.
Okay.
I'm pretty sure you're correct. I don't know if it's been by convention, but one of them determines the other ones.
Yeah, because they are not like linearly independent, the first
Right.
3, if I remember correctly. And another question here, now that you have all the Bravais lattice, when you said that the 200 family has inside also the 100, if we take the second cubic lattice, so
Right.
the body center, here the 100 wouldn't be in the family of the 200, because on the 200 we have just 1 atom in the center, and the 100 we have the 4 atoms.
So that would be that plane, the plane that is passing through the middle right here, right?
Yeah.
That contains that lattice point. That plane, one of its neighbors is right next to it, would contain this 4. So what I mean is that they're not identical. I just meant that the whole family of 200s passes through all of those planes in between.
Okay, but because I usually, like on my side, when we talk about planes, when we say it's within a family, we mean that there is basically no difference.
Okay.
Exactly. But in this case, the 200 would be different from the 100.
Yes,
At least there would
exactly.
be some. Okay.
Yeah. All right. So I'm just saying that the planes are contained one inside of the other, not that they're identical. Okay. So coordination number I covered, how many atoms are nearby. And the most important thing is that the body center cubic has 8 and the face center cubic has 12 points near it. Now, the next thing I want to cover, because I'm going to give you a problem about this, has to deal with the packing factor. So if we take our volume of atoms in the unit cell and divide it by the volume of the unit cell, assume that the atoms are spherical, right? So what happens is that you put 4, let's say you put 8 to make a simple cubic, you have a space in between that is empty. You put 4 balls touching with each other on top, 4 balls touching with the 4 on top on the bottom, and then you still have a void in the middle. So you can look at how much is empty in the space in between them. And if you look at that, this is what you would get. This is the simple cubic. You have this 4 on the top, this 4 on the bottom. And if you start making these balls bigger enough so that they touch, you have that the circles, the 2 spheres are touching, you're always going to have a void in the middle. So what that translates to is that the simple cubic is not as efficient as if you had put a ball in the center and then started increasing the size to see how much of the volume is occupied with your atomic system versus how much volume is empty. So let's look at the other one. This is the simple cubic. You can visualize the void in the middle. And the packing factor here for the simple cubic is 0.52. So that means that the radius going from here to here is 1/2, because going from here to here is another 1/2. And then you can calculate the volume of the sphere, the radius cube times 4/3 pi, divided by the volume of the unit cell, which is a cube, which is just a cube. You see the a cubes cancel out. There's one atom in your unit cell, and that means that you get this number, 0.52. So now if you do the same thing, but for the body center cubic, you see that this ball is completely inside of the unit cell, and then you will have this little 8 octets around it, right? In this particular case, for the BCC, which is what a lot of metals take as the lattice that they like to be in, the question would be, what is the atomic factor, right? So you can do the calculation and you end up with 0.68. And then the idea is that between this corner and this corner, there should be 4 radii. And you can do the geometry, because going from here to here, all of these sides are A. Going from this corner to this corner is just a square root of 3 times A. And once you put the unit of the volume cell here, and you put that there's 2 atoms in your unit cell now, but the radius of the atoms that you're putting there is this much, you get that the packing factor is 0.68.
Is it not 3 atoms? Why is it 2?
Oh, because there's 8 octets on the corners, plus this one that is complete. So that's why it's 2.
You complete, oh, you think of those 2 extremes as 1? I see.
No, as 1/8 in this corner, 1/8 on this corner, 1/8 on this corner, 1/8 on this corner, and then another 4/8 on the bottom, plus the 1 in the center.
Oh, it's just not shown. I see.
Right, not shown, yeah. So once you do that, you get those 0.68. And then I have another one that would be for the BC. This is the body center cubic. If you're doing the face center cubic, you will have a face, half of the ball in each of the facets, right? And then 1/8 of the ball in all of the corners, and you can do the math for that one too. All right, questions?
So will the atoms say if we have a packing factor of 0.8 or 0.7, how will that be how will that shape the properties of some metal which has the packing factor of 0.3 or 0.2?
So the packing factor properties, usually the atoms pack themselves in the most efficient way that they can. So if you look at it, the one that has the most filled unit cell is the one that a lot of the minerals go into. However, the only place where that is not the case is when it's more efficient for a particular unit cell, because of the way that the atoms are bonded to each other, that they take on the other ones. So a simple cubic one could be the case, because that's the type of ionic bonding that ionic bonding helps make it more stable.
Thank you.
All right, let me tell you, I have a couple of, let me go back over here. I had to fast forward to the next point in the PowerPoint. So here, oops, let me go back. I'm gonna give you this is the sodium chloride structure. The sodium chloride could be a unit cell that is cubic, but this is actually the one that sodium chloride likes to be. And if you look at it, there's, let me bring out the laser pointer. There's one atom in each of the corners that is sodium. And then there's an atom that is sodium again on each of the faces. 1, 2, 3, 4, 5, 6. So that means that sodium chloride is sodiums on the FCC lattice, and then there's a displacement because you would have that the chlorines are also in an FCC lattice. I don't know if you guys can visualize this. So you have an equal number of sodium and chlorines, and then alternating in this simple cubic lattice. You could think of them as alternating in this simple cubic lattice so that they always have 6 nearest neighbors. You can also see the planes happening through here. Like for instance, there's a plane here, there's another plane here, there's another plane here, and that plane keeps going in that direction. So if you were to cut it through this plane, you would be seeing a surface that was all chlorines, right? If you cut it through this plane that is passing like this, you would see something like this, where you would see sodium and chlorines on that particular chlorine idea. Here's a sodium chloride crystal. You probably had some in your lunch today. And then the structure, if you remove all of the red chlorine ions, you're left only with the blue ones, and those are the FCC unit cell. So the sodium is also in an FCC sublattice. So that's the crystal structure of sodium chloride. So this gives you a bit of the visualization for you to see what kind of unit cell you're dealing with. So it's a face-centered cubic Bragg lattice with a basis consisting of the sodium at the 0, 0 position, and then the chlorine at the 1/2 displacement of the original. So a bunch of salts have this particular structure like this, like lithium fluoride, sodium bromide, and so forth. For this kind of systems, that's one of the most conventional approaches to see it.
So can we represent these crystals with just a 1D array? Because if you see, there are the same lines of 1 chloride, 1 sodium, so on and so forth, like in our horizontal, in each axis is the same structure. So
maybe you're thinking if whether you can represent a plane like this, but no, you need the whole full thing to the full unit cell to represent the crystal, right? You can represent a plane out of it and see that, yeah, there's this plane versus this plane and so forth, and see which are the atoms that show up the most.
Okay, thanks.
Then another structure that is interesting is this one. This is cesium chloride. Again, the cesium chloride is also a cubic lattice. And here you also have that cesium and chlorine are the same number, so it's 1-to-1 ratio between the two. And you can think of this one as each ion has 8 neighbors of the other kind around it. So you can think of this one as a BCC lattice, body center cubic, where the center ion is different from the nearest neighbors. And if you shift it so that the other one is the one on the center, it looks the same. They're identical to each other. So here you have simple cubic with a basis of the cesium at 0 and a chlorine in the center. You could look at it like that, like this is just a simple cubic lattice with 2 atoms on its basis set. And
Dr. Bunda,
yeah.
I was wondering, so I look at those images, but honestly, I don't really understand what they are. For example, the colors we see, the sodium and chlorine you showed, or with the orange and the blue ones, are these clouds of electrons that is represented as a sphere in this case?
It's
Or
the
what is it
atoms.
exactly?
It's the atoms, like the position of the ions. And you have this space filling thing, but it's not the size of the, it's not the radius of the atom. It's just the sphere is just to represent the space that would be taken up by the atomic cloud, but it doesn't have to have this particular shape.
If all of them are spheres, then there will be some kind of gap between them, right? Although we try to put them. So is that what's happening in reality too?
Yeah.
Or,
yeah, and that's kind of like what you see in the STM pictures that, for instance, we were seeing today in the colloquium, right? Except that they're not really spheres. They can have different shapes. We just use these color spheres because they're easy to see.
Are they like really rigid when they make a contact, like sodium and chlorine, right? Are they that strong that even if they have this strong force between them that pushes them together, they still don't bend or don't change?
It's really hard for them to change because they have a really high Young modulus. Yeah. This is another representation of the same thing, right? That you have 8 cells of them together. And you can see here the little cube on the center that is the one that is the simple cubic with one on the center, different color. I think that's the one that I wanted to show you. Here's another one. The most important one is the previous one. Here's another one. This is a hexagonal. And there's a close packing of the hexagonal that is really good too. So you can think of, you can calculate the one for hexagonal, how much close packing you have, PCC and simple cubic. And you'll find that the hexagonal close packing is one of the best ways for arranging the atoms, because one of the atoms is sitting in the hole of the other 6 atoms above it. I don't know if you can see it here. But for instance, when people were traveling and they had to put the cannonballs, they would arrange them in this hexagonal close packing structure because it was the one that was more efficient for packing. All right, so let me go back now to talking about Bragg diffraction, because it's I want to finish XRD today. And some of the aspects that we just talked about, like for instance, cesium chloride and such, are what I want to use as examples right now. All right, so now I'm gonna share my iPad screen with you guys. Hopefully it doesn't glitch. So one of the most important things that I need to cover is Bragg diffraction. So we actually have the Laue condition in the previous class. That's what Laue came out with. And Bragg diffraction is actually a little bit after Laue. So I don't know if you guys are familiar with the story of Bragg. There's actually 2 Braggs to talk about. Is anybody familiar with it?
No.
I know about the English guy who went to World War I think. I don't know about the other guy.
Yeah, so you're thinking of the son, I believe.
Yeah, I heard about the oh, so you're talking about the father's son. Yeah. So the other Bragg is just his father. I think they both won Nobel Prize for their
Yeah, so the story is like this, look. So Bragg, the father, was in Australia, I think for being a faculty member or something like that. And then his son was born in Australia, but he's British too, right? So I don't know how British in Australia works or anything like that. So maybe I'm just not familiar with how it works. But the idea was that the first thing that I found interesting is that the younger one, they're both named William Bragg. The younger one broke his arm playing with a bicycle. His dad went to the lab. He had heard about Rothenberg and the X-ray discoveries, and he used X-rays to set the arm of his son that was broken because he had the bicycle accident, right? So this is one of the first times that X-rays was used for medical issues. So this is around the 1899 or something like that. So now von Laue, which is who we talked about before, and his experiment where they actually were able to see the condition that we talked about, the Laue condition, when is it that you get a scattering and so forth. That was a really important discovery because it proved that X-rays were actually waves. So the nature of the X-ray was not really well known. It was discovered, but it was not well known. And then von Laue proves that they're waves and that these are waves just like sound waves and light waves that get diffracted, and they are getting diffracted by atoms, right? Which are now proven to be real things, not just the imaginary things that our Greeks philosophers were thinking about. So now the story goes that Bragg Sr., who's a faculty member now in, I believe, Cambridge, he moved back to the UK, right? And when he's a faculty member, he actually was on the side that X-rays were particles. He thought X-rays were particles. Now his son is really smart guy. He starts as a mathematician, but then decides to move into physics because physics is more interesting. He went to the same school. So that's why I believe it's Cambridge, because he had a Trinity fellowship as an undergraduate, or maybe the equivalent of what we think undergraduate, and maybe it's not undergraduate. And as part of it, he had to write a thesis. And he had just heard about von Laue's experiments and how X-rays are waves. And the other thing is that he had also was familiar, because he's a physicist, he's familiar with optics things and the laws of reflections in optics. And he's walking, thinking about what he should be doing for his thesis, and he comes up with an idea. He realizes that there's only a few reflections that could happen due to the law of reflection. Only a few directions are going to be important when the X-rays are diffracting from the planes of the atoms. So he goes, writes down the equation and develops it. Exactly the same things that you would see in optics at that time, classical optics. And he comes up with the idea and then realizes that this is how the planes would be reflecting the X-rays, and which are the conditions. This is more important than the Laue conditions, because now they could prove something. And then he goes to his father, who's the experimentalist, and his father rigs up the machine to do this experiment, which basically is the first X-ray powder where you have to rotate the sample, and the detector is called a goniometer. This is what the X-ray powder does when you're doing this kind of experiment. And they get XRD going for different materials. So now his father, the faculty member, goes and writes the paper about it and presents it to their academy, the Royal Society of Fellows, or whatever it is. And then he wrote, and here's the equation which is due to my son on the paper. Can you imagine that? That's what he did. He said, pam, 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 this is all that I've been doing in the lab. And then I can use this equation due to my son. He doesn't even put his name on the paper. He doesn't even call him by his name. He just write, and my son who came, and I thank my son for coming up with this equation. And then thankfully the son also got to share the Nobel Prize. But I think that made the son not be very happy with his father.
Yeah, I think that's why he decided, yeah, I'm just going to go to war and die because my father doesn't love me.
So yeah,
Must have been an
the
interesting
fortunate thing is
Christmas
that his
dinner.
father and him share the Nobel Prize. He's the youngest person to get the Nobel Prize, at least in physics. Maybe there's somebody who has gotten it in another area younger, but he was 25 when he got the Nobel Prize for what we call the Bragg refraction.
Yeah, I think there are some other people in Nobel Peace Prize who are younger, but I think in physics, Bragg is still the youngest. 25. I'm 25.
You're 25?
Yeah, 24 and something, I think, yeah.
Yeah.
I still have 6 more months, so maybe I'll do something.
So now we would look at scattering from the planes of a crystal. So let's say we have the HKL plane of a crystal. So the idea is as follows. Let me start. This is your plane. It's supposed to be a straight line right there. And then I'm going to have my incoming radiation is coming in this direction, is hitting that plane right there. And then there's an angle, let's call it theta right here. So this is my incoming radiation, the X-ray, right? This is the incident wave coming to the plane. It has this arbitrary angle theta, and then it gets scattered and reflected by the crystal plane. This is my scattered wave in that direction. And it also has an arbitrary angle. In this case, let's call it phi. What I also know is that this plane has a direction that is normal to it. So let me write this as the normal direction. And if I took this blue line or purple and converted it, it's right here, right? More or less. So this right here, can you guys see the line? I'm trying to make it a dotted line.
Yes.
This is negative ki. I'm just translating that vector in that direction. And if we do that, it turns out that there's a vector that goes from here to here. This is the Q vector. So questions about this geometry? All right, so we have the allowed scattering condition, and the allowed scattering condition tells us that Q is gonna be Ks minus Ki, scattered versus incoming. We also know that, and this is what von Laue told us, right? So this is the plane in the HKL. And it turns out that that Q vector that I have up there is actually the same as this G vector, right? What that means is that the Q and the G are the same thing and they should match up with each other. But now we also know that from the previous class that this G is actually normal to this vector. It's actually the normal to that plane, right? That unit normal is in the same direction to the G plane. So what that tells us is that since Q is equal to G, right? Then the two angles have to be equal. So theta is equal to phi. So this graph is not correct. This theta and this phi angle have to be the same so that Q is right on the normal. And then further, we have that the two angles are equal and that the sum of the two vectors are making an isosceles triangles. So we have the law of reflection from optics. So that would be how we get reflection from the planes. All right, so this is my first equation. Let me call it 1. And let's rewrite 1. Now let me do some algebra. And actually, let me write Ks dotted with Ks. From 1, I have that is Ki plus G HKL. And then I'm dotting it with itself, right? So vector Ki plus the G vector. And when we dot Ki with Ki, we actually get Ki squared. And then we have twice Ki dotted with G. And then we have the magnitude of HKL squared. So if we assume elastic scattering, so that means that both of our angles, both of our Ks and Ki are the same magnitude, different angles. Then we know the magnitude because lambda is the wavelength of our X-rays. We know that the K vector is just the 2 pi over lambda. So that means that I can look at this guy and rewrite it. So I'm working with that one and I see that, remember, there's a Ks square on this position and it's the same as this Ki. So those two cancel out. And I just have to deal with this one. And from that term, I get the -2 Ki dotted with G HKL. And what that is the magnitude of Ki. So that gives me a 2 pi over lambda times -2. So let me put that 4 pi over lambda. And then the angle between J and K, cosine of the angle, and let's look back over here. So I'm dotting this one with this one, right? So I need the cosine of that angle. So that would be this monster HKL. So that's the other magnitude times the cosine of that angle that we talked about, which is 90 degrees minus theta. Okay? So the cosine of 90 minus theta is just sine. And I have 4 pi over lambda. The magnitude of J, of G, sine 90 is equal to J HKL squared. So we see that there's the both magnitudes on both sides. And then,
Dr. Brenda?
Yeah.
Would there be a negative in front of that? The negative
sign is from the -2 Ki.
Yeah.
There is, but I have the square here. So you mean from here to here, right?
Yeah.
Since this guy is a square and it's a magnitude square, I think I can get rid of it that way, but maybe I'm missing something.
I think comes from the cosine.
Yeah.
90 minus theta is minus sine instead of sine.
Exactly. That's probably where I lost it. Yeah. There we go.
Okay.
And then if you look at it, we did this last time where we look at what is this quantity right here, right? This one, the G square.
First 90 minus theta is positive sine theta, I think, because it's the first quadrant that's positive. I think it's somewhere else, the negative sign.
But it's also a positive quantity, right? So it's just a sign.
Yeah, yeah, it should be a positive quantity because it's a modular square.
Yeah.
So yeah, we can figure that out later, but yeah.
All right. So the most important thing though is that, and this part is from our previous class where we look at that and we have the 2 pi over DHKL is also equal to this G square vector. So from all of that, we have a lambda over here. Let me rewrite it. And the 2 pi's are there and so forth. And I can rewrite it as 2, this distance between planes, sine of theta. And this very important equation, I'll label it 2, is what Bragg wrote for his dissertation, for his thesis. So this very important equation tells you what Bragg scattering is. Questions?
Okay, this is from the last lecture, but can you remind us a little bit what G was? Because the G vector was.
Is the direction of G. All right, so the direction of G is the normal to the unit vector, and the magnitude of G is the spacing between planes. So this is what we wrote on the previous class. This magnitude, right, is the same as this inverse distance between the planes. That's what the magnitude means.
Oh,
then
we can't see the.
Sorry?
We can't see your screen. We're only seeing the.
Oh, sorry. I stopped sharing my screen somehow by mistake. iPad, go.
We can imagine.
Well, you can. I can't. I'm not. I don't have very good imagination.
Let me go back over here. There we go. So this is what I had written in the previous class. That's the magnitude of G. So yeah, so here, let me write this out just for completeness. So having this guy here and this guy cancels one of those guys, and I have that this is my whole 2 pi over D on the bottom. Okay. And that was the magnitude of G was in the discussion in the previous class.
Okay.
So this Bragg scattering law is really important and it's highlighted right here. So let me redraw this now correctly and show you the planes and the idea that Bragg saw when he was walking near the pond. So let's start with a family of planes. Let's say that there's a plane right here, and then there's another plane right here. Okay? So the spacing between those two planes is this DHKL. Questions? All right, so then we have that there's a incoming plane wave in this direction, and it's coming in that direction, and is given by this incoming wave right here. So we know it's a scattering of there, and that plane has the G vector right here. All right, I saw something in the chat, but I don't have if I click on it, it will take me off my.
Oh, we're still talking about the sign, the
Okay.
negative sign. But yeah, that's probably because it's not 90 minus theta, but it's probably 180 plus theta. But yeah, that's a minor thing.
All right. So then there's from in the other vector and the other plane, there's also this incoming plane wave and has that direction. And if we look at our scattered wave, it's going to come out in that direction. And we also have another direction here. Same scattering, everything here. The angle here is theta. And if we compare if we extend there, we're going to see that this right here is 2 theta. That's the angle there, right? Between Ks and the Ki coming out in that direction. Questions? So what happens is that the first ray Ki, the first wave vector Ki coming in, is gonna hit that plane and keep and scatter into that direction. The second one has actually this additional part right here and this additional part right there. So it's gonna be traveling that much more. So the first one, this one, is traveling at this point right here. It's a scattering right here. It's a scattering of that plane. And this same one is gonna, when that one scatters, it's gonna keep traveling this direction, then scatter, and then it's gonna travel this direction, this distance, sorry, traveling in that other direction before reaching the detector. So this area that I highlighted in orange, that length that I highlighted in orange, is the path difference between scattering on the top plane and the one below it. Does that make sense? So what we have then is that for a particular wavelength, this DHKL sine theta, this path that is traveled here is just that one, right? Is this DHKL sine theta. And you have two of those paths before the two wave vectors catch up. At this point, from here to here and here to here, those two vectors are identical. But the one on the bottom is going to carry this extra portion of length that it traveled. So then you get constructive interference if the path difference is equal to a multiple of the wavelength. That's the key thing that Bragg came up with. So our path difference is this right here times 2 because there's two of those. So if you don't have a multiple of the wavelength, then you don't get constructive interference. So that's the most important thing. Bragg law is now used to determine crystal structure from powder. And what you have to do is that you have to have a monochromatic beam of X-rays. Then you have that the monochromatic beam of X-rays is directed at the sample. When you have that the sample is powder, what that means is that you actually took a crystal and you broke it apart into tiny little pieces, so tiny that they're like a little powder. But what you're doing is that you have a sample that is now a multitude of samples all identical to each other because they're almost the same size powder. And this powder is oriented in all the possible directions. So then you have the X-rays coming in, the X-rays coming out, and you're sampling all of the possible directions. And then what you're changing is the direction of your detector. By rotating the detector around this sample that is pulverized, you're capturing only the important 2 theta angles that would have a lot of constructive interference.
So when in the case of powders, since it's random, so I guess most of the overwhelming number of X-rays that hit the powder don't do the interference, but only a few of those would do that because the planes of the crystals are totally random.
Right. So you have this geometry, right? You have your sample here. You're gonna send X-rays in this direction, so that's your Ki. And then you're gonna be sampling with your detector in this direction like this. So that gives you the 2 theta vector. And what you're doing is that maybe one of your crystals is oriented just exactly out of the tens of thousands of crystals that are in your powder.
Exactly. So that's why, I think you mentioned that in one of the other classes, the why powder is better. So in case of powder, the initial angle can pretty much be any random angle because there should be, out of all those random directions of the powder particles, at least a few of those should correspond to the right direction of plane with your incoming direction of X-ray. Okay, that makes very good sense. Yeah.
All right, so now looking at the Bragg law, what we have then is that we use a monochromatic mean for our X-ray generator. So that means that this lambda is known, right? Because it's gonna be monochromatic. That's the key part, that is lambda is known. You're setting up the angle and you're finding at what angle you're gonna get intensity versus no intensity. So you know this one, you know this one, that way you determine this D. Whatever you get signal is because that was one of the Ds. Questions there? So now you have a way to determine whether you get D spacing because you know both theta and lambda. And with that, now you just have to investigate whether you have what is the Miller index that you're seeing.
Can I ask a question?
Yeah, go ahead.
Yeah, it's regarding the powder thing, because I can see why we would get a peak if we had a perfect single crystal, and when we hit the specific angle, we get a lot of scattering, otherwise not. But let's say we have two crystals close together and they are 10 degrees rotated with respect to each other. So wouldn't we see the same pattern for crystal A, the same for crystal B, just 10 degrees shifted?
If everything else was the same, you would. So here's the thing. This is a 3-dimensional angle that you have to have. So basically this is your sample, right? Yeah. You have this rotation to take care of. That's one angle. And then you have this angle. That's another angle. And then you have this angle.
Okay.
All right. So by doing that 2 theta experiment, you're just probing one angle with the other two being completely random.
Yeah.
So you had a single crystal and you align it correctly so you have, I forget what the other two angles are called, but let's call them phi and psi or something like that, right? So you rotated this angle perfectly. You rotated this angle perfectly. Now you have the two are just two different crystals would be that they're just off by a little bit in this direction or this direction. They would constructively interfere at the right 2 theta angle. So you actually have to worry about 3 angles being correct. So now if you have a multitude of little crystals, then maybe there's 10,000 or 10 million little powders in there. little grain boundaries. And one of those grain boundaries, just randomly, if you have enough sample packed in together, is going to have the right two other angles so that when you're probing by just theta, you hit the right two other angles and get a signal out.
Okay, but wouldn't we hit those angles at different thetas?
No, because the theta is set up by the experimental. I think I know what you're assuming, right? So you're thinking there's one that goes like this, and there's one that goes like this.
Yeah.
And you're thinking, okay, there's this one and there's this one, and then there's a theta between them like that. That's what you're thinking, right? Therefore, when I shift by one, I'm gonna get the other one.
Yeah, exactly. So like when we are hitting, we are hitting both of them, and at some point we would see the peaks at the theta difference between the two crystals.
So the reality is that this one and this one wouldn't be the same. But if you had aligned those two together the same, then that's actually what Laue did, where they just changed one of the axes a little bit and then they saw the rotation based on that axis. But in this case, you have two different axes that are going to be pretty hard for them to be aligned together. So it's what you're thinking makes sense in terms of having the same crystal, same orientation, just one this way and the other one this way. And that's pretty hard to get. But what you have is that the geometry is the one that determines in what direction of all the other possible geometries are.
So we are, if I get that, we are basically testing only the ones that we have G normal to the plane. Okay, all the others will maybe scatter a little bit, but nothing of importance with respect to the one. Okay, yeah, because they go to zero. Okay, yeah, that makes sense.
Yeah, so very few would be leading to a maximum in this case. All right, so I have about 10
Excuse me.
Yeah.
In case of I have still confusion about in case of very thin film, like yeah, I mean in that case only the region, like just we don't get the average of that scattered wave. That's why we don't able to get like that XRD pattern. That's only the reason.
I think that's the case, and also your X-rays are not going to get enough ensemble average, and also your actually I don't know, but I think it's just
like yeah. For example, like our film, like which is very thin, like in case of it's nanometer, so we are not able to get. I mean, yeah, we are not able to get like that XRD, but I mean,
exactly.
that's why.
Yeah, exactly, because you're not able to ensemble average in that direction.
Yeah. Okay.
I actually have two pages of notes. I think that might take me a little bit longer than the 5 minutes that I have left. How about we stop right here? And next class, I'll cover a little bit faster. And I don't know if you guys have questions aside from those. So we have covered most of what, so we have covered all of what Laue did in his first try. And then we have Bragg's Law, which is really important too. And then the next thing that I want to cover is what happens, how come you get missing reflections sometimes? And this is actually what Laue found. He thought, I am finished. Here's the, Von Laue said, I'm finished. Here's the peaks that you should see. Is this what the experiment, what the film saw? And then they saw that there were some reflections that were missing because they were using a copper salt that was a little bit more complicated, and it wasn't just one single atom in the unit cell. So for those, I can cover those in the next class, and that's called missing reflections. For this, are there any other further questions?
I think two people have their hands raised in Zach and Zachary.
All right, go ahead.
Thank you, Armand. I was wondering, the wavelength that we have, we can't really change it from the XRD device, right? So the only parameter we have is this angle change.
Right. So
and then we'll be able to find this D.
Yeah, your XRD device is powered by sending a high voltage into probably a copper. I believe it's copper. I don't know if you're thinking about the one in the 5th floor. Is that the one you're thinking about? We have an XRD device in the 5th floor of physical science.
I didn't use that, but the principle should be the same, I hope.
Yeah, so for instance, if you have copper, it looks at the K alpha transition. And that means, I think, that you get lambda to be 1.5 Armstrong. Because you're looking at what transition, one of the possible transitions for copper.
So my point is this lambda and angle, they are directly correlated. But since one of them is constant, we are only able to change the second one.
Right. So we know lambda.
Right.
So let me give you an example of what an XRD experiment is going to look. So here you have that this is 2 theta. And let's say you started at 20 degrees and you would have 20, 40, 60, 80, 100, 120, right? So then your XRD is gonna look maybe something like this. There's a peak right here and it's really big. And then there's another peak here and it's really big. And then there's a little peak right here. And then there's another peak right here. And then there's another peak. And there's some background there, so it's not perfect, right? There's still some background. And what you have is that this intensity that is happening, the intensity is related to what plane you're in. So what you were changing is this 2 theta. And if you have an intensity, right, is because when you were passing through that powder sample, once you hit that particular angle, there's a path interference that happens to those X-ray scatters that add up to so much. So I don't know if that's your question. So go ahead.
Oh, yes, that was my question. But also to continue the Babu's discussion, what is the limit for this D to be measured?
The limit for what? Sorry?
The limit on the height or the width of the material that can be measured.
So if you're doing...
So what is this D's limit? Yeah.
Yeah, so if you're doing powder, you have to have tiny little crystals that are micron size, right? What you guys do is you deposit a single layer of atoms. So your samples are maybe 10 Armstrongs thickness. So you won't be able to see those. But if you have something that is a micron thickness, like a micron size crystals, then you can see them. If you deposit something that is 100 nanometers in width, you're not going to be able to see it correctly. There's another technique though, that what they do is that this is your film. And then what you do is that your X-rays come at a really low angle right here. So this is the angle that you would have there. And you just do this profile, very low angles, and that can tell you how much material you have deposited because it's coming in at a low angle. But it's something that is a little bit different technique.
Can we use other electromagnetic waves which have even lower wavelength? Maybe those you can use when your sample size is really small, like 100.
Yeah, actually, if you use neutrons can tell you even smaller.
Because in principle, this is true for any electromagnetic wave, right? I mean, we're just talking about X-rays, but it should be the same for any electromagnetic radiation, I guess.
Yeah, you can change that.
I mean, if you can change the lambda, yeah,
by going to another X-ray source. So, for instance, I don't know if you guys are familiar with Argonne National Lab.
Yes.
little bit.
So I believe in argon they have so different places have it too. Like for instance, there's an advanced light source, and what they do is that they shine electrons into a crystal, and then the X-rays come out, and they have super high energies. So you can probe
very low
smaller wavelengths.
Okay, yeah, that would probably work.
And that would prove the electronic interaction with the electron cloud. If you go with neutrons, the interaction is between neutrons and the nuclei. So now you're probing a different kind of system, not the electronic cloud, but actually the protons, where the ions are in the system. So neutrons also give you more information about your system too. Yeah. And then the last thing, let me just wrap it up here, is that then you have to identify, for instance, you could say, I have a crystal, and this is probably the 110, and this is the 211, and this one is the 220. But that's where you identify based on what your assumptions are about your crystal. You might say this is the distance, correct distance for the 110 plane for my zinc oxide particles that I made, you know? But you just identify them from knowing what are the possibilities that you have and whether you could see it or not.
So the Miller indices are assumptions.
Are assumptions that are well educated, because if you make a system, you kind of know what is the unit cell that you would have that crystal be made of. Now, you might not know
Also,
exactly where they should fall, because the unit cell of your crystal might be a little bit different, but you are able to tell what you're making.
Also, I'm so sorry, Zachary. Last question. So this, I was always trying to understand this. Why didn't they use theta instead of 2 theta? Why, for example, the graph, why is it in terms of 2 theta?
Oh, it's just that the angles are set up in your goniometer. That's that 2 theta is the angle that you're measuring, and it's because you're comparing this with this one with this one.
I see.
Yeah, but that's the main reason.
Okay, thank you.
All right, so I think that's all my time for today. Zachary, did I get your question?
Yeah, I think actually like what Zach asked got most of what I was asking. So
all right, go ahead and ask it. I'm not in a hurry.
Oh, I was just thinking that if you go back to the theta graph that you just had up, I was just thinking if you have like the planes all have different distances. So like I was just trying to picture what like when you scan through the theta, like one peak, some peaks will be closer to other peaks because like the 211 will be like won't be equally spaced from the other one.
Exactly. So there might be another one right here and another one right here. Yeah, I was just speaking at random.
Okay, yeah, but other than that was it.
Can I ask one last question?
Yeah, go ahead.
So if the powder gives the always like average is equal in every places, why we always get the like intensity peak shift whenever we are doing XRD?
Why do you get a shift? All right, so there's two reasons for it. One is that the machine is not calibrated correctly. Okay. So that could be the reason for your shift. And then the other one is that you're making things. So the way that a lot of people do it is that they have, let's say you come out with an XRD pattern, and then you compare it with a database.
Yeah, it's shift somewhere. Yeah.
Right, and then the shift could be because it's not calibrated correctly, or because the sample that you have is a little bit tiny difference from the one that is in the database. So let's say you were making platinum, you have platinum crystals that you put in there, right? Maybe your platinum crystals have a small discrepancy in the unit cell size of your system compared to the one that is in the database. So that could be the reason for the shift, that you're shifted by 1% because your unit cell is off by 1%.
Oh, I see.
And it could be off by 1% on average because you have impurities in your materials that you were growing with. Or maybe it's because you're off because your device is not calibrated correctly. And that's what gives you the little bit of difference. But usually is that you have a different unit cell size difference, and this peak might not be exactly where it should be because the database says that this peak should be actually here, and you're off by 0.1 of a degree.
Thank you.
Since you said that you're not in a hurry, I'm kind of going to ask one last question, which is, so when we derived this formula based on the, the classical optics and the ideas of interference, so we see that this is kind of like the lowest multiple. We have to have lambda equal to 2d sine theta, but it can also be multiples of that, right?
Yeah, that could be multiples. In fact,
yeah,
the other multiples are going to be coming out because you have another crystal over here, right?
Yeah.
And then that crystal is going to be coming down this way. So now you have to account for this much.
Yeah, exactly.
The 4 and the 8 and multiples of that. So those multiples are the ones that are always going to show up as interference.
Oh, so we can, yeah. So I think that answers my question even before I actually asked it, which was that I was going to ask that if we have another element or material which has exactly the double D value, then how would we differentiate between those? Well, I guess we can do that, but just by seeing the consecutive interferences and seeing that, okay, I think we can do it that way. But that would have been my question, that what would be the difference between, if you have one material with a certain value of D and another material with an exact double value of D,
right,
then,
right.
But yeah, we can do consecutive interference and see that how the separation is between consecutive interference and how the D value changes.
Right.
Then we can do it. Okay. Yeah.
All right. Well, you guys have a good weekend. Stay warm. We're almost out of this freezing, right?
Yeah, I don't have warm water for 2 days in my apartment, so I hope it's over soon. I haven't taken a shower in 2 days.
All right.